Good morning, students. Welcome to Physics 1101 lab. For today's lab, you will be conducting a basic experiment working with vectors. In order to understand vectors, it's important that you understand what an equilibrium vector is, as well as a net resultant vector. To aid you in your understanding of vectors, the goal this week is to use a force table to balance several forces so that the equilibrium and net force vector are shown. You'll be using a force table, such as the one simulated here in decimals. You'll notice that for our force table, angles start at the positive x-axis as 0, and they go counterclockwise all the way down to 360. Each vector will have a corresponding magnitude as well as a direction on this table. This is as though we are looking at a bird's eye view downward at the force table. Each force will be represented in lab by a string supported by a width system and a pulley at the edge of the table all the way around. This will be more apparent as you come to lab today. Your job is twofold. You will be demonstrating that a single vector can be decomposed into component vectors along the x-axis and along the y-axis. These are considered basis vectors. Any vector that is oriented along the x-axis is the basis in the x direction. Any vector that is along the y direction is the basis in the y direction. So given any vector or force or velocity around this table, we can always find its projections along the y-axis and the x-axis. Any vector can be decomposed into these two components. As a demonstration, let us consider the vector that is oriented in the positive first quadrant at 80 degrees. And let's suppose that its magnitude is 3 newtons. You'll notice that the red arrow represents our vector F1. What would its corresponding components be? How would we determine that? The way we would determine it is we would first determine the angle that F1 makes with the positive x-axis. In this case, it's 80 degrees. So we would want to take the cosine of 80 degrees and multiply it by the length of F1, and also the sine of 80 degrees and multiply it by the length of F1. As follows. Pull out your calculator. Make sure it's in scientific calculating mode. Punch in 80 degrees, then choose the cosine, and then multiply that result by 3 in the case of our vector. And so we need a vector that has 0.520 or 0.521 magnitude along the x direction. So the angle along the x direction will be theta 2 equals 0, and the magnitude will be 0.521. So you'll notice that the tip, if I were to draw a line directly from F1 down to the x-axis, it would meet the tip of F2. Now we do the same thing for our velocity vector, or not our velocity vector, our y component. We would take 80, multiply that, or take the sine of that, then multiply that by our 3, which is our magnitude, and so we get 2.95. So we need a vector that has almost the same magnitude as our normal vector, just slightly off by a few units, 2.95. Okay, and now what angle would this vector have to be oriented at? It should be at 90 degrees. So we go 90 degrees, and now we have our two components. The green component is our x component, The blue component is our y component. On your force table, you will not be able to put F1 in the same quadrant as F2 and F3. Instead, what you'll be demonstrating to me in lab is the equilibrium vector. The equilibrium vector is the one that equilibrizes, basically makes equilibrium achievable on the force table. And since we're dealing with actual forces, each vector being suspended by weights hanging off this table, in reality, this situation will produce a net force on this ring such as to pull it in this direction. Instead, we want this ring to be balanced around the center. And so we want a force that is essentially the equilibrium to this. I'm going to get rid of F1, and you'll see why in just a moment here. I'm going to put the angle at 0. And now on this app, I can actually show the resultant net force, which is exactly right there. If I want the equilibrium vector, I just need to take 180 degrees from that. So 180 plus 80 would put it somewhere down here in this quadrant. In fact, that's shown there. So this is what your force table would look like if you were demonstrating this in reality. The issue that you're going to run into in this lab is that we are dealing with weights. We're not dealing with masses. So each time you try to suspend a mass from the pulley system, you need to be working with 9.8 divided out of that. Okay? So rather than working in forces, we can actually work in masses because each of these suspended systems would be divided by 9.8 to give us the mass. So that's one thing that you can do right out of the gate. So in this lab, there's two procedures. The first is you're going to be converting this polar vector, force vector, into component form using mass instead of newtons. So we would divide this mass by 9.8. I want to see all of your work in that conversion in your notebook. I want you to just verify that this is in fact the correct component form by using the Pythagorean theorem as well as the arctangent of the inverse of the ratio of your two components. Once you have that, I need to see that your force table is in the correct orientation. And so you'll follow these instructions to set that up. Once you have that, you'll need to sketch a figure in the results in your notebook, and then you're ready to move on to the second part. The second part requires you to break 3 vectors down and then add those together to find the net result or the sum of the vectors. So basically you'll have an X and Y component for F1, an X and Y component for F2, and an X and Y component for F3. You'll add all the X components together and all the Y components together, and that will get your net force in rectangular form. You'll need to convert that back to polar form in order to put that on the force table. After you've put it on the force table, I need you to show in Desmos the same thing. Actually, we'll probably just be rid of that requirement this time around, and we'll just show this on the force table and sketch the diagram in your notebook. But that is your orientation for today's lab. We will explain and discuss more of this when we get to lab today. Until then, have a great day. We'll see you later.